is the sound hole of my guitar. But there's a very different hole at the center of our Milky Way galaxy, and that's a black hole. See, a black hole is a rupture in the fabric of space and time itself. And black holes were first predicted almost a century ago by none other than Einstein himself. In 1915, Einstein published his famous field equations for general relativity. Just 6 months later, a young German man by the name of Karl Schwarzschild found a solution to Einstein's solutions that not even he predicted. That solution is now known as the Schwarzschild solution, and it predicted the existence of this rupture in space and time itself. It predicted the existence of black holes. Now, for a long time, physicists thought that black holes were nothing more than a mathematical fiction. But in the late 60s and 70s, things began to change. Astronomers began to turn their telescopes to the center of our Milky Way, and they found the stars at the center of our galaxy moving way too fast around an object way too dark for it to be anything other than a black hole. And not only a black hole, but a supermassive black hole, billions of times the mass of our sun. And then in the late 70s, Stephen Hawking revolutionized our understanding of black holes by publishing the three laws of black hole thermodynamics that established an exact equivalence between the three laws of thermodynamics and the laws of black hole mechanics. Just like there was a law of entropy, a second law for thermodynamics, there was likewise a law of entropy for black holes. And then just in this century, in just the last decade, in 2019, the Event Horizon Telescope collaboration created the first ever image of a black hole. And that was a black hole Sagittarius A star at the center of our galaxy, as well as M87, a much larger black hole farther away. And now a new revolution is underway. Physicists are now trying to exploit the information paradox to gain some insight into a potential theory of quantum gravity, which would be a marriage of our two most fundamental theories of the universe, quantum field theory and general relativity. That's where my research comes in. My research begins with a very simple thought experiment that attempts to combine general relativity with quantum mechanics. And here's the thought experiment. Say you have a black hole. We all know that a black hole has an event horizon. Trespass that event horizon, and that's a one-way ticket to the singularity of a black hole. It's a one-way hotel. You check in, you can never check out. Now here's the question. We know, of course, of Hawking radiation emitted from the black hole. In other words, a black hole is not really black. Perhaps it's better thought to be of as gray, okay? Because a black hole, as Stephen Hawking showed in 1974, has this intrinsic temperature that's inversely proportional to its mass. Now, how can you tinker around with quantum mechanics when you're near the gravitational fields of a black hole, when you're in the Schwarzschild metric? Well, one thing you can do is you can bring in a famous experiment from quantum mechanics, and that is the double slit experiment. You see, in 2018, a group of researchers found that if you have not a double slit, but a single slit, and you have atoms falling into the black hole, physicists found that these atoms produce an entropy, a radiation that's completely distinct from Hawking radiation that they called H bar, horizon brightened acceleration radiation. Now, if we account for diffraction effects of these atoms going through the single slit, and then we introduce a double slit, so not one slit but two slits, then how does the interference pattern created by the atoms going through this double slit interact with the Hawking radiation on the other side? Now, this is a very deep, non-trivial physics question that attempts to bring in two completely separate experiments. One is a black hole, a gravitationally massive body that requires general relativity to describe, and one is the double slit experiment. It takes a quantum mechanical experiment and tries to make it interact with a general relativistic object. And so the goal of my research project is to see, is there any distinct form of radiation that occurs from a double slit experiment placed near a black hole? And is there any kind of distinct entropy generated by this by a series of atoms that are infalling through these double slits? So that's it. Thank you for watching this pitch for my research. I hope you find it interesting, and I would be very honored to present my research at Brown Symposium.